Hello everyone. So this is the first week problem solving session. So we will start from the definition of function and a different type of functions we will see, and then we will solve some problems regarding functions, and then cardinality and countability we will cover, and we'll solve some problems. If you have any doubt or any question other than your assignment questions, you can post in the chat box. Am I audible to everyone? Okay, so let's start. So the very basic thing is function. Uh, what is a function? As we know that in everything, in especially in mathematics, everywhere we have used the function. But what is the definition of function? Function means a function. Let us say f, which maps two set a and b, and it will map every element of a to a unique element of b, right? Or we can say that function is an expression, rule, or law that defines a relationship between one variable to another variable. Let us take some example. Okay, so I'm writing in OneNote, and this presentation and OneNote file will be shared to you. Okay, so first thing is function. Okay, so from here we can see that example of a function. Let us say that x is an element in a and y is an element in b. A and b are two sets, and if x is equal to y, then we call that y is image of x and x is pre-image of y, right? So let's assume there is a set A and B. Okay, and we will take some example also. So let us say in generalize that there is two sets A and B, and x is an element which belongs to A, and y is another element which belongs to B. And now the thing is, and we consider that f of x is equal to y. This is written here, but in detail, if we go, let's assume A is a set of 1, 2, 3, 4, 5, 6. Okay, and B is another set. Let's assume 2, 4, and 6, and 8 also. Okay, now if we say that f of x is equal to 2x, or y is equal to f of x is equal to 2x. Okay, now if x is equal to 1, which belongs to set A, okay, fine, or we can put, then what will be 1 corresponding to x is equal to 1, y is equal to 2. So, and 2 belongs to B, set B. So can we say that f is a function? Yeah, sure. Now we will come to the different types of functions. Basically, we will divide the function into 3 types. One is injective, another is surjective or on to, injective means 1 to 1, and bijective. And the third one, bijective, is very important. Why? Because you will see the use of bijective in cardinality and countability also. Although all are important. So let's start from injective.
Hello. I
Yes.
have a question.
Yes.
Like, you can go to the.
Can you speak little louder?
Oh yeah. Can you please go to the previous
In slide?
2x 1.
Yes.
No, one note.
You are not audible at all.
One note. Is it audible?
One note. Okay.
So here its function is from A to B, right?
Yes.
So this will not F will not be a function because 5 is not related to anything, right?
Okay. Yes.
So in set B there is no element for 5 or 6 for that.
Yes.
So this will not be a function really.
No, I have taken it only 2, 4, 6, 8. It will be more.
Okay, fine.
Just I
Then
have seen you one example for x is equal to 1, and for the rest also there will be some
there will
image,
be
right?
oh yeah, I thought
Yes.
that is fine.
It is also not up to 6, it is up to more.
Okay, okay. Then it's fine. Because you oh, yeah, now it's good.
Yes. So now come to injective function. These are very basic things. What is an injective function? An injective function in mathematics, we can say that if there is two set A and B, okay, so each item in set A can only be matched with one item in set B, not more than one, and no two different item from set A can be matched to the same item in set B, right? So for example, we can see this. Look at this. If A have four elements, A, B, C, and D. B have four elements, 1, 2, 3, and 4. So this look at the first image. We can say that this is an injective function. Okay. To the second, this one. A has three, one, A, B, and C, and set B have 1, 2, 3, 4. Now look, from set A is mapped in A, element A is mapped with 1, B is mapped with 2, C is mapped with 4. But there is no pre-image of 3, right? In another word, we can say that y is the image, 1 is the image of A, 2 is the image of B, and 4 is the image of C. But there is no pre-image for 3. But these two are injective functions. But if this is the case, A has A, B, C, and D 4 elements. B includes 3 elements, 1, 2, and 3. And A is mapped with 1, B is mapped with 2, and C and D both are mapped with 3. Come to the fourth example. Same thing is here. A is mapped with 1, B is mapped with 2, C and D both are mapped in 3. But 4 has no pre-image. So basically the thing is, if there is any element in set B which does not have any pre-image, then so in these two cases we can see that there is no pre-image, and in these two cases we can say there is no such element which don't have any pre-image. But the where the confusion arises, that sometimes students say that, or that if there is no pre-image then it will not be injective function. Not like that. There may be some elements which do not have any pre-image, but if two elements have same image, in that case it will not be injective, right? So injective, that's why we call it one to one also. Okay, now the second thing is surjective or onto. A function f from A to B can be said to be onto for if for every y in the codomain B there exists an x in the domain A, such that if x is equal to y. No issue. So in another language we can say an onto function, also we are calling it surjective function, is a special type of mathematical rule that connects two sets. Let's call set A and set B. So in an onto function, every element in set B has a partner in set A. That means that the function covers all the elements in set B and there are no leftover in set B without a matching element in set A. Come to this image. From here, you can understand in better way. So our second thing is surjective or onto. Okay. How many students are there? Okay, fine. Come to the surjective function. Surjective functions, as I have already explained in this slide, from here by the images we can explain that. Look at image 1. A includes 4 element ABCD. B includes 4 element 1, 2, 3, 4. And every element in set A has a image in set B. Now come to the figure 2. A has 4 elements ABCD. B includes only 3 elements 1, 2, 3. And A is imaged with 1, B is mapped with 2, C and D both are mapped in 3. These two we can say surjective function. Now come to figure 3. If A includes 3 elements ABC, B includes 1, 2, 3, 4. And now you can see there is one element 3 that do not have a p-image in A. This we will not call surjective function. Now come to figure 4, ABCD in A and in B 1, 2, 3, 4. But C and D are mapped with only single element in B 3 and 4 is left out. 4 do not have any pre-image in A. So these two, this figure 3 and figure 4 in sub figure you can say, this is figure 2, sub figure 3 and 4. These are not surjective, but these two are surjective function. Now come to bijective function. What about bijective? Bijective is the combination of injectivity and surjectivity. So from here we can say a bijective function, which is also known as sometimes bijection, ensures a perfect match between two sets, typically referred to as set A and set B. To be considered bijective, function must satisfy these two properties. Injectivity we have already read, surjectivity we have already read. Okay. If a function if satisfies all conditions of injective and surjective functions, then function f is called bijective. Okay. Now these are some examples. This is a bijective function ABCD 1, 2, 3, 4. A is mapped with 1, B is mapped with 2, C is mapped with 3, D is mapped with 4. This is bijective function. But what about these three? A is mapped with 1, B is mapped with 2, C is mapped with 4. 3 is left over, right? So if there is any leftover element in set B, then it will not follow the rules or properties of surjectivity. Now come to sub figure 3. Here A, B, C, D, 4 elements are in set A and B in set B 1, 2, 3 is 3 elements. B and C are both mapped with 2. Similarly, in this ABCD are 4 elements, 1, 2, 3, 4 are 4 elements. C and D are mapped with 3 and 4 is left over. So these 3 are not the cases of bijectivity. This is only bijective function. Right? Now, before coming to the cardinality and countability, the question we will ask that when are two sets A and B same set? When we will call that if we have two sets A and set B, then when we will call that these are same size, right? Please think Anyone left to admit? No. Okay. So before coming to this, let's solve an example first. Let's say there is 4 relations. Okay. -4, 3, 6, -3, -2, 3, and -1, -. These are 4 relations. Okay. And let us consider that the first element is from set A and second element is from set B. So the question is, can we say this relation a function? Is it a function? Yes, we can say this is a function. Why? Because for each element in set A, there is a map in set B. Or if we say that these are the input, -4 is the input and 3 is the output. If 6 is the input, 3 is the output. If -2 is the input, 3 is the output. And if 1 is the input, -3 is the output. So if this is the relation, we can say yes. The answer is yes. Now, the question is, if there is another relation, let us say -2 minus and 2. Okay. 3 -2 -2, 3 and -3 -1. Okay. Now the thing is it a function? If this is the relation, the same question is this a function? Or in other word, we can say whether this relation follows the definition or follows the rules of function. The answer is no. Why? I'm giving you 2 minutes to think about this. Please think. Then if we are saying this relation is function, then why we are saying that this relation is not a function? Anyone? Please think.
-2 is related to 2 and
Yes?
-2 is related to 2 and
Uh, can you speak little louder?
-2
Yes,
is
-2.
to both 2
So
and
yes, very good. Now let us map these two relations. Okay? Let's, it is A, B. What was, it was -4, 6, -2, and -1. And what was B? 3, -3, 3, and again -3. Yes. So if we map this, we will get this. That A has 4 element, -4, 6, -2, 1. And B has 4 element, 3, -3, 3, -3. So this is a function. Now map this. This is set C and this is set -2, 3, -2, -3. It is 2, -2, 3, -1. Okay, -2 is mapped with 2. But -2 is mapped with 3 also. If we write only 1 -2, then it will be more clear for you. -3 is mapped with 2 and -3 is mapped with -1. So if this is input C, the element of C are the input, and output, let's assume Y. Let us call. If X belongs to C and Y belongs to D, and Y is equal to f of X, whether this condition is getting satisfied for a particular f X, that is 2 -2, there is 2Y, right? We can get 2 also, we can get 3 also. So this is not a function. Now another relation we will take. -1, 3, 4, 1, -1, 2, 1, -3. Whether this is a function, the answer is no. Why? Let's map it again. Let's call it A. B is another set. -1, 4, 1. Here we will get 3, 1, 2, -3. So from -1, there is 2 image, 3 and 2. from 4 is mapped with 1 and 1 is mapped with minus 3. So again, this is not function, or this is not following the relation of a function, right? So we'll cross this. So function you understand now? Now come to the question I asked earlier. There are two sets, set A and set B. So when we call that set A and set B both are of same size, so your answer may be like this, that when they have the same number of elements. For example, if A includes 4 elements and B includes 4 elements, so we call that there is same number of elements. So these are of same size, right? But now let us define some sets. Set A includes 1, 2, 3, 4. Set B includes A, B, C, D. Set C includes alpha, beta, gamma, and xi. And set D 1, 2, A, B, alpha, beta. So now ask 4 questions. Whether set A and B are of same size, whether set B, C are of same size, whether sets C and D are of same size, and whether sets A and C are of same size. Is there any question? No. You people, please write the answer of these 4 questions in chat box. I'm giving 3-4 minutes, okay? No answer till now? Still 2 minutes left. Please take 2 minutes, think that whether these are of same size or not. Why I am asking this? Because okay, first you answer this, then think about this. That if something is not countable, any set is not countable, then what will be the meaning of same size? right? Let us do first this one. You take 1 more minute and answer. Okay, fine. So first question is whether sets A and B are of same size or not. Yes, definitely. A has 4 elements, B has also 4 elements. Whether B and C are of same size? Yes. B includes 4 elements, C includes 4. C, what about C and D? No, these are not of same size. Whether sets A and C are of same size? Yes, A and C are of same size. Basically, A, B, C all includes 4 elements, so these are of same size. This is different. Okay. Now, the same question if I ask that A includes 1, 2, 3, 4, B includes A, B, C, D, C is the set of all natural number, and D is the set of all real number. Then what is the answer of the same 4 questions? Let's see whether sets A and B are of same size. Yes. It includes A includes 4 elements, B includes 4 elements. But what about B and C? What about C and D? We can generally see that B includes 4 elements, A, B, C. But C, it is the set of natural number. That means 1, 2, 3, 4, and up to an infinite number or n number, whatever you say. Then B and C are not of same size. But what about C and D? And what about A and C? You think and answer. At least one of you should answer this question, that whether set C and D are of same size. This question 3 is very important. You take 3-4 minutes or max 5 minutes, think and answer here in chat box. Yes, anyone?
Yes, sir. C and D both have infinite numbers in natural number set and real number set. So can we
Yes,
say that C and D are of same size?
that is the question I asked. What do you think about this? First, tell that what do you mean by natural number? Okay, step by step, let us answer this question. What do you mean by natural number? And what do you mean by real number? Okay, natural number means simple. If the counting numbers 1, 2, 3, 4. Okay.
Yes, sir. Integers, all integers.
Yes, but there is a little difference. We can include 0 also, right?
Yes, sir.
And okay, and come to the integer that we normally denote with z. That includes all positive numbers, negative numbers, and 0 also. There is rational number also, right? What do you mean by rational number? Any number that can be expressed as a ratio of
In
an integer.
in a ratio.
Yes, and there is irrational number also, like pi, root 3, like, right?
Yes, sir.
Now, whether natural number is a subset of real number.
Yes, sir.
Let us ask this question. If n is the natural number, is it a subset of real number? Okay, fine. This question will be answered soon, because now if we directly cannot say that whether set C and set D are of same size or not. So now come to the question of cardinality and countability. What does the same size mean? Right? Think about it first, that if we are saying that let's assume there is two set 1, 2, 3, 4, B is the ABCD. These are of same size. Whether the same size, and if I say that C is the all set of natural number and D is the set of real numbers. Now the question is, what does the same size mean? Now here the concept of cardinality appears. We say that two sets are there, A and B have same size or they're equicardinal if there is a bijection F from A to B. If this is the case, then we can write that set A and set B are equicardinal. We normally mathematically we write like this. There are some more symbols, some people like in different way also, like mod A is equal to mod B, like not mod, in that symbol. So if A and B are finite, then A and B are equicardinal. If and only if A and B have same number of elements. This is the same thing in this example for A and B, the same thing for the example in this ABCD. But now the question arises that if A and B are finite set, then we are saying this. What about a set of infinite numbers? So now the question comes, what is countably infinite set? It is very interesting question, that what is countably infinite set, right? Can anyone answer this? What is the meaning of countably infinite set? We are saying countably infinite. If is it like there is infinite number of elements or something else? Can anyone answer this? Take your time, 2-3 minutes, think about this. The question is written here. What is countably infinite set? And what do we call countable? If we are saying that if a set is countable, then what does it mean? Whether it is finite number, it includes finite number of elements, or whether it includes infinite number of elements. Think 2-3 minutes and answer. So you understand the question, right? There is two questions. What is countably infinite set? And the second question is, if there is a set, let us call set A, and we are calling it countable set, then what does it mean?
Sir,
Yes,
when a set has a bijection with natural number set, then we
yes,
can say it as a countably infinite set.
yes, right. Bijection of natural number. So now, if a set, let's let us call set A. So you are in uh, from BTech, MTech, or which course?
Sir, BSc.
BSc. Okay, which college?
Yes, sir. BSc Maulana Azad College, Kolkata, Statistics Honors.
Okay, 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 good. So if set A is equicardinal with n, right? N is the set of all natural numbers. Then we call that A is countably infinite set. So what is the natural number here? The point is that if we are saying that n is the natural number, a set of natural number rather, and there is a set A which is countably infinite, and we are saying that set A is countably infinite if set A is equicardinal with the set of natural number, right? So what is the set of natural number here? Think little deep. What is the set of natural number and why it is required? because now we will solve some numerical problems regarding cardinality and countability, and we need to know the meaning of this, right? Basically, what is infinity? If we say that natural number n has infinite number of elements, right? 1, 2, 3, and all. There is z also, that includes all negative and positive integers, and 0 also. There is rational number, there is irrational number, all has infinite number of elements. So here, if we are saying infinite, countably infinite, it means that it has infinite number of elements with some reference, and the natural number n is the reference here. And if set A is equicardinal with set n, then we will call it countably infinite set. Now, second question. If we are saying, let us say that set A is countable. What does this mean? When we will say that a set A is countable. If set A is countable, then what does it mean? Someone was answering, Onindita, right?
Yes, sir.
Can you answer this? If set A is countable, then when we can say that set A is countable?
Sir, again we can say set A has a bijection with natural number.
Only this, or there is
Um,
any other condition also? Let us say with some example. Okay, let's define A. Whether it is countable?
yes, sir.
Okay. Whether this is countable?
Yes, sir.
Okay. Whether this is countable? If set A includes all natural numbers, or you can write like this also.
Sir, this is countable, but the
Hmm.
points are infinite.
Yes. So this is the thing, that set A is countable, and there may be two cases. If set A includes some finite number of elements like 1, 2, 3, 4, ABCD. Look, this, if we are saying that this is the set A includes 1, 2, 3, 4. It does not have a bijection with natural number. Whether it has?
No, sir.
No. Because come to the definition of bijectivity. If this is the bijective functions, all the elements of set A must have a image in set B, and all the element in set B must have a pre-image in set A. So if we are saying that set A is 1, 2, 3, 4, then it doesn't have a bijection with the natural numbers, but still it is countable because it has finite number of elements, right? If A is
Yes, sir.
ABCD, then also it has the finite number of elements, so it is countable. And if A includes all the natural numbers, then the elements are infinite, but countably infinite. So it is countable. So the what are the conditions to be countable? One is finite number of elements. Condition 2 is bijection with n. If any of these two conditions are satisfied, we will say that the set is countable. Now, let us come to an example. If a set is E, which includes the positive even integers, so can we call it a countably infinite set? There is a set E is set of this is the set of positive even integers. So is it countably infinite? When we call a set is countably infinite, to answer this question we need to know this. Just before few minutes we have discussed that a set is countably infinite if a set A is countably infinite, then A has a equicardinality with the set of natural numbers. And what are the natural numbers? One from, if we start from 1, 2, 3, 4, and all. So now, what is the answer of this question? If E is the set of all positive integers, is it countably infinite?
Yes, sir.
Yes. So how? Let us see the solution. What the natural numbers includes 1, 2, this is the set of natural numbers, and if we write the set of E, that includes set of all positive even integers 2, 4, 6, 8, and all. Now let us try to map this. We can map this like this. And all, because E also includes an infinite number of elements, N also includes some infinite number of elements, and we can map 2 with 1, 4 with 2, 6 with 3, 8 with 4, and so on. So the answer is yes. Or in term of mathematics, we can say like this, that f is a function where n from there is a set or function from n to e, and fn is equal to 2n. So it is countably infinite. Now, the second question is the set S of positive integers that are perfect squares. Is it countably infinite? S is a set which includes the positive integers, and the second condition is perfect square. Like 1, 4, 9, n square, and so on. The question is it countably infinite?
Yes, sir, this is also countably infinite.
Yes. Similarly, we will map this S 1, 4, 9 and so on. There is the natural number set of natural number rather, 1, 2, 3 and so on. We can map like this. We can map the element of set A. Let's assume 1 is mapped with 1, 4 is mapped with 2, 9 is mapped with 3 and so on. So the answer is yes. Now come to another question. Z is a set which includes like this: 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4 and so on. The same question: is it countably infinite? Is it countably infinite?
No, sir, this is not countably infinite.
Sure.
Um,
Think again.
okay.
Let us say this was the first question. E was the set of all positive integers. So we could write f of n is equal to 2n, right? This we can write f of n is equal to n square. Now, what about this? There is two questions. First, how will we map this, and how will we define this? Take 3-4 minutes, try to write it down in your copy, and then I will write it here, and then you will match whether it is correct or not. You think 2-3 minutes. And try to write, and then I will write it the answer and you match. Okay, let us write it. Z is the set of all integers. Now, let us define it as a function first. F of n, we can write like this. If n is even, and if n is odd, we can write like this. Now, let us try to map. And this is the set of natural. And so on. We can map like this. And so on. Z is the set of all integers, positive and negative. So 0 is mapped with 1, 1 is mapped with 2, minus 1 is mapped with 3, 2 is mapped with 4, minus 2 is mapped with 5, 3 is mapped with 6, minus 3 is mapped with 7, and so on. So it can be mapped with the natural number, rather a bijection we can find here. So it is countably infinite. Actually, there is no difference between this question and these two questions. The basic concept of all three questions are same. If we are saying that the set of all positive even integers are countably infinite, just because we can map this, rather we can find a bijective map between E and N, then here if S is the set of all positive integers that are perfect square, and we are able to find a bijective map between S and N. Then similarly, we are able to find a bijective map between Z and N, where Z is all integers and N is the natural numbers. So this is also countably infinite. Now we will come to another example. There is set A. Let's define it like this. A such that n belongs to Z. Z means all integers. And the condition is 0 less than or is equal to n less than or is equal to 5. This is set A, and there is another set B. Meeting is getting recorded. Okay, fine. We define it like n belongs to Z. Z is the set of all integers, including positive and negative, even and odd, minus 5 less than is equal to n less than is equal to 0. There are two sets. Now, the question 1. If we define a function from A to B, whether is it a bijective function? Question 2. Whether A and B are equicardinal. Or we can say like this. First, let us answer these two questions. If A is a set where n belongs to Z and condition is 0 less than is equal to n less than is equal to 5. And B is the another set where n belongs to Z and the condition is minus 5 less than is equal to n less than is equal to 0. Now we define a function from A to B, whether it is a bijective function, and the second question is whether A and B are equicardinal or not. So let's define A first. Now the first question, function A to B, whether it is a bijective function or not. Can you answer?
Sir, if we use mod, then there is a bijection.
Okay, but okay, you are saying that if we use mod, you mean if x belongs to A and y belongs to B, then y is equal to mod x. Whether you are saying this?
Yes, sir.
Okay, so if this is the condition, then there is a bijection. Anyone else?
Yes, sir.
Whether there is any other student attending this? Okay. No, not like that. You are thinking very good, but this is not the answer. If y is equal to mod x, then all the elements will be equal. But it doesn't mean that it will form a bijective function. Why? Until and unless we define the function, we cannot say that whether it is bijective or not. If we say that y is equal to mod x, yes, there will be a bijective function, no doubt. But if we do not define anything, or if we say y is equal to minus x, where x belongs to a and y belongs to b. If we define y is equal to mod x, then you were saying it will be bijective function. What about if we define y is equal to minus x? Will it not be a bijective function? Yes, it will be. So there will be different definitions also. So only from this question, if f is defined from a to b, we cannot say anything that whether it is bijective function or not. But we can definitely say the question number 2, that whether a and b are equicardinal or not.
Yes, sir. Both have same number, so they are
Yes,
equicardinal.
yes. So there is a bijective function from a to b available. There is two options, whether you can say y is equal to mod x, or whether you can say y is equal to minus x. So, and from a to b we can map like this, so it is equicardinal. 0, 1, 2, 3, 4 and 5. And what about b? Minus 5, minus 4, minus 3, minus 2, minus 1 and 0. So you can map like this also. In any another way also you can map. In reverse way also you can map this. So whether it is yes. Now come to another example. Whether I have discussed this. Countably infinite set fine. J. Okay. If we say that there are two sets, one is real number and Another set is 0 to 1. All the elements of 0 to 1. So can we say that these are equicardinal? Same cardinality?
Sir, again, set 0 to 1 is a subset of real numbers. So they are not equicardinal.
Okay. Okay. So if we map it like this, or if we say that 0, 1, this is the set base, 0, 0 0.1, 0 0.2, 0 0.9, now 0 0.01, 0 0.02, and so on. Can we map this like this from 0 to 1? Not this, because we are not considering 0. From 0 0.1 we are starting. So if can we map all the element from 0 to 1 to some element of R? Yes. And there will be infinite number of element between 0 to 1. So it will be of equicardinal. The answer is yes. Now come to another example. If A is a set, it is the similar example of previous one, that N belongs to Z. Condition that -7 less than is equal to N less than or is equal to 0, and set B is N belongs to Z such that five less than N less than 8, whether A is equicardinal with B. So let us map it first. A is from -7 to 0. And what about B? So if we map like this, so you can see from here that A and B are not equicardinal, or the cardinality are not same. Now there is another question, that whether set A and set B can map any bijective function. The answer is no. And if this is the mapping from A to B, then it is clear that this is not a bijective function, right? Now come to another question. This is very interesting question. There are two sets. Set A what is set A and set B. A is A1, A3, A4, and so on. And there is a set B. Set B includes the elements B1, B2, B3, B4, and so on. So now there are three questions. Question 1, whether set A is countably infinite. Whether set A is countably infinite? Anyone can answer? Can you answer?
Sir, I think no.
Yes?
Um, so there is infinite number first of all, and the um, natural bijection is natural number is missing, I think. Is it right?
No, not like that. Look, uh, whether if there is A1, A2, A3, A4, or let us assume some set is C, 1, 2, 3, 4, and so on. Look, it doesn't mean here we treat A1 and 1 with equal value. Here 1 is a number, A1 is not a number, right? But both
Yes, sir.
are element of a set. If A1 is the element of A and 1 is the element of C, but both are the element. So the first question is whether set A is countably infinite or not. Can you answer this? From this three set, there will be 3-4 questions I will answer now one by one. And there is a interesting concept also in this question. That is why I am solving it. What do we mean by countably infinite? We can move to our previous slides, right? Here we have answered what is countably this. What is countably infinite set? If there is a bijection between set A and N, or you can say if A and N are equicardinal. So whether there is a bijection between set A and N, let us try. And so on. Now in four and so on. So there is a mapping, like A1 is mapped with 1, A2 is mapped with 2, A3 is mapped with 3, A4 is mapped with 4. So there is a bijection mapping between A and N. So we can say that A is countably infinite. Fine. Now question 2. We need some space here, so let us create it. Okay. The question 2 is whether set B is countably infinite.
Yes, sir.
Good. Infinite. Okay. Set B is also countably infinite in the similar way. Like we can map B1, B2, B3, B4, and so on. And natural number is this. One, two, three, four, and so on. Now we can definitely map like this, where B1 is mapped with 1, B2 is mapped with 2, B3 is mapped with 3, B4 is mapped with 4. So we can say that set B is countably infinite. Now there is an interesting question. Let there is a similarly set C will be also countably infinite. Now if there is a set let us assume this is set S, which is A union B. The question is whether set S is countably infinite. This is the question. If set A is one A1, A2, A3, A4, and so on, set B is B1, B2, B3, B4, so on, up to infinite, then A is countably infinite, B is countably infinite. Whether A union B is also countably infinite, please think about it. Take 2-3 minutes and answer. Or I will answer it now. Take your time 2-3 minutes and think. Set A is countably infinite. We are defining. We are saying that set B is countably infinite. So whether set S, which is A union B, is countably infinite.
Sir, I think A union B will also countably infinite because
Yes,
both of them are countably infinite
yes,
individually.
yes, this is the thing. So how can we write S? S will be A1 B1, A2 B2, and so on. So if we map it like this, A1 B1, A2 B2, and so on, and there is a set of natural number n, 1, 2, 3, 4, and so on. Then A1 belongs not belongs to, A1 is mapped with 1, B1 is mapped with 2, A2 is mapped with 3, B2 is mapped with 4, and so on. So the answer is yes. S is countably infinite. Okay. Now question number 4. Let's say if A intersection B is phi. Phi means null matrix or a function with no elements. Sorry, a set of with no elements. So let us name it as earlier was S. So let us name as T. So whether T is countably infinite. Think about it. We will solve 2-3 more questions. We will try to solve within the time limit. We have 9 minutes left. So if T is A intersection B, and if we say A intersection B is a phi that is set with no elements, then whether T is countably infinite? The answer is no. Obviously, it is not, because T has no elements. T is not countably infinite. Now, from this example, what we are getting, that if a set is A, if a set A is countably infinite, if another set, then their union will also be countably infinite, right? But what about their
Yes, sir.
intersection? It depends. It depends that whether their intersection will be countably infinite or not. It depends on the condition. That here we are saying that if A intersection B is phi, and phi indicates a set with no elements, then it is not countably infinite. Okay. Now come to another question, and it is also a very interesting question. Let let us say a set is A. Okay, and A is ln n, such that n belongs to set of natural numbers, that is mathematical n or math, whatever you say. And we are also making a condition that this is the subset of R, natural number. So the question is whether A is countably infinite. Can you answer it? Take 1-2 minutes and think.
Sir, is this A is uncountably infinite?
Uncountably infinite A?
Yes.
No. It is also countably infinite, because look, n is the set of all natural numbers, capital N, and n belongs to capital N. Now, what can be the elements of A? If we try to map, what will we get? Or rather, let us write in a different way. A we can write ln1, ln2, ln3, ln4, and so on, right? So if we try to map it with n, can we map it like this? ln1, ln3, ln4, and so on. This is the set of natural number, capital N or capital N, whatever you say, 3, 4, and so on. We can map it like this. And look, there is no difference between this mapping and this mapping or this mapping. These are all similar mapping, right? So A
Yeah.
is countably infinite. So A is countably infinite. This one note sheet will be shared with you also for your revision purpose and all. So now let us quickly take another example, that there is a relation. Let us say set A is like that. Five n comma minus 3n, such that n belongs to Z, all integers including positive and negative. So whether A is countably infinite, answer is yes. How? Look, if A is a set, like this is the relation 5n comma 3n. If we say n belongs to Z, Z can be positive, negative. So what A can be? A can be like 0, 0. A can be 5 minus 3. A can be minus 5, 3, and so on. Why 5 and minus 3 and minus 5 and 3 both? Because n can be 1 and minus 1 both. So this is countably infinite. So here we stop this for today. In next session, we'll discuss some more topic and question answer.
Thank you, sir.
Let us, yes, let us stop recording. Okay.